Okay, students, let's begin lecture and welcome back. Um, this is the 8th session, so can you bring that down a little bit? It's a little too much. No, the microphone. It's a little too hot. Okay, the uh, the today's lecture is session 8, so we basically had 7 sessions worth of instruction out of 28. Now, 28 meetings for this class. So it just feels like we just started, but we're about a fourth of the way through the semester now. Oh my goodness. And so your quiz that's coming up is going to be over the first 8 lectures, including today. Here's the SARC Tutoring hours, and you may find it very, they don't have anything on Monday. So tomorrow but you do have something this afternoon. So try to use that strategically for your studying, because I'm going to give you a pretty big study assignment. And in addition, there'll be more over the weekend for you to work on. Do you have learning center hours?
Yeah.
Tomorrow or today?
It's today and then Monday.
Okay. Can you just announce that?
Oh yeah. Hi guys, I'm the LA here in case you didn't know. And
one of the two LAs.
Oh, one of the two. Sorry about that. And I have office hours at the physics help room, 158, the same room that Dr. Lee has his office hour. Today from 12 to 1, and then on Monday from 4:30 to 5:30 p.m. Yeah.
Good. All right. So those will be some extra study availabilities for you to get ready for the quiz. Now let's talk about that quiz. It's going to be next Tuesday, 18 points as per the syllabus. And the breakdown on points is following. First of all, you're going to have one problem for 12 points, just like, so homework points or a homework problem that I grade for 12 points is going to be like the problem. And I'm probably going to grade all of these. In fact, Tyler, you're not going to have to grade any of the exam. It's going to be Dr. B all the way. So I'm going to be grading like a maniac. So then you'll also have 6 multiple choice items, and you'll use your iClicker 2 for those. So those will be like A, B, C, D, or E, and I might put in one simple calculation so you could type in a number. Now on an exam or a quiz like this, when you're using the iClicker, you'll be doing something called self-paced polling, self-paced mode. And you'll have all the questions, and as soon as I start the clicker base, like right now, you can get a Go Nitro. On Tuesday, when you get the Go Nitro, it'll start you at question 1. All right, and then you can type in, the letter A, B, C, or D, and then hit the send key. And then you go to the next number, and I'll give you the instructions for exactly how to do that. You use the arrow keys that are on your iClicker too. It's pretty basic. It's kind of like typing in alphanumeric data. But you'll go at your own pace. So unlike class here where you go at my pace, I control the pace. But on Tuesday, you'll control the pace. It's pretty basic, and it'll be just a few multiple choice items. Don't worry, and some of those will be equation matching, formula matching. Okay, so maybe 2 or 3 formulas, and then you'll have a set of formulas and then a set of concepts, and then you'll match them. So don't worry about memorizing formulas. I know you guys in engineering, you get a lot of pressure to do that, but I don't want you to memorize formulas. I just don't. And it's a quiz, so it's fairly simple. So the equation load is not going to be that big. The thinking load, however, is going to be ginormous. All right, it's going to be a lot of pressure, and I have some more comments about that. Now, we're going to start at the beginning of class, so we'll get every. So don't be tardy on Tuesday. Okay. Now I'm the last one to say don't be tardy because I've been tardy the last couple of weeks just about every day on account of my bad leg. But we'll have a little bit of a few minutes of preamble, and then we'll do it. And then after the quiz, we'll do some lecture. And if you want to double your studying enjoyment, we're going to be in chapter 5 after the quiz. That's Newton's laws of motion. So we'll be, we've been talking about forces and stuff informally, but we'll start the formal Newtonian mechanism or the Newtonian formalism after the quiz on Tuesday. So that's chapter 5 in our free textbook. And by the way, over the weekend, I'm going to be commenting up and annotating up the textbook. And so, I know I won't be done by tomorrow. I'll be doing it all through the weekend. So just keep studying in the textbook, and especially my annotations, because they give you an idea of the things that I'm thinking about. They're my commentary on the textbook. Okay? And nobody writes a perfect textbook. And so my comments are helpful to you to figure out what I think is important in the textbook. Matter of fact, there's a comment in there about a formula that I never use. And a bunch of you guys did use it, I think, on homework 2 or homework 3. The one with VF squared minus VI squared equals blah, blah, blah. I never use that one. Never. But if you think about it, if you look at it carefully, it's basically related to conservation of energy, and we'll get to that in a few weeks. But now, last thing about number 3, at the beginning of class, don't be late. If you get here after the first person finishes, you may not take the quiz. Let me repeat that. So take your finger out of your nose, stop, get your nose out of your phone, and listen. If you arrive after the first person finishes, you may not take the test. All right? So we got a little bit of leeway. I'll be blabbing my big mouth for a few minutes to start. I'll give you some admonition and whatnot. But if you get here so late, now we'll have 30 minutes for this, but I guarantee you the first person will be done in 10 minutes. All right? Guaranteed. All right? And the thing is, the first person that finishes in 10 minutes, that's not always an A student. Matter of fact, it's frequently not an A student. A students take a lot longer. All right? So you want to be an A student. You want to crush this thing like a bug. All right? And so, but there's going to be but at least one person, and my prediction is, in a full 1 hour test, it's usually 20 minutes. For this one, I'll predict 10 minutes. All right? And so if you come late after that guy, whoever it is, you're toast. Or as they say in Latin, SOL, which is a Latin word, a Latin phrase that means toast. Yeah.
Okay, so you said if you come in after the first person, is it turns it in, or is it like finishes it, or like locks it up?
Those are all the same thing.
It's like, I feel like if we finish, we should just like wait till I get
If you come in the door the minute that he gives me the test up here, you could take it. But if you come in 5 seconds after that, you're SOL. Right? So Steve, you're part of the invincible too. I mean, that's your heritage. But I don't know where the other one is. But so be invincible. Be here on time. All right. Just saying. All right, now, any questions about this? We got a few more things to talk about, but about this, anybody else? Let's bring this table up, and I'll sit on the stool. Come on, give me the stool. I'll sit on this for a while. All the way up. And I just feel like getting a bird's eye view here. Okay, so no questions? Let's continue. All right, now what you want to bring is a regular calculator like this, no programmable calculators, and you cannot use your cell phone either. All right, so no cell phones on the test. Can I see your calculator? Yeah, so one of the Fantastic Three, no, the Spectacular Three. So one of the members of the Spectacular Three has a TI-30XA, which is not solar, it's battery power. Okay, that's a TI-30XIIS, whatever that means. Anyways, they're both pretty inexpensive. Get one over the weekend and you'll be squared away. What's that?
It's like something instrumental.
Yeah. Definitely know how to use your scientific notation on it. And also your trig and your inverse, so your inverse sine, inverse cosine, inverse tangent, in case you have to calculate that. I'm not saying you will, but you might. Make sure you know how to do that. Steve?
Are we in radians or
Degrees.
degrees?
Actually, I take that back. We're going to be back and forth, but I'll tell you when we're in radians. Okay? Because we're going to talk about circular motion a little bit later today. And when we get to that, I'll be doing radians, not degrees. But I mean, we'll be talking back and forth about it. But doing oscillators, it's good to be in radians. But like trajectories like that we've been doing, degrees is fine. I don't see any, I never see anybody, well, aim it at 0.24 radians. They always give you the degrees, so. All right, so when they, in Star Trek, when they set the phasers, to destroy the Klingons or whatever, they don't go radians, it's degrees.
Yeah.
Degrees starboard, degrees port, etc. iClicker, I've already mentioned it. Make sure you got good get some energizers or Duracells in there. You don't want it to flake out on you. And the batteries that come with the iClicker when you buy it, are El Cheapo batteries, and they're notorious for flaking out in the middle of a test. You don't have permission to keep talking. I'm eyeballing you for a reason, so that I don't have to be yelling at you. But please take it. When I'm eyeballing you like this, I'm waiting for you to zip zap, right? So your iClicker, make sure you have good batteries in there. Pencil and eraser. I always try to use, one of these, second grade pink erasers. Those are, especially on Scantrons. So you're not going to be using Scantrons on the quiz, but the midterm you'll be using a Scantron. And so those things, especially the cheapo pencils that you buy like at the bookstore and stuff, 10 for $1 or whatever they are. The erasers on those can be really bad, and they'll tear up a Scantron, but these things won't, these little pink jobs. Now, what do you want to study? You want to study everything. Study everything. And as I've mentioned, The annotations will be helpful. And actually, all the problems, as I mentioned before, work out all the examples and stuff you can in chapter 4. And that'll kind of guarantee that you're also covering the previous chapter concepts, because it all kind of builds up there. All right. Now, before we go and talk about our classwork, we're going to have some classwork. Can you see if there's enough blank paper? And if not, go down to Ray and get some. Before we do that, I want to go over some common errors that I saw on the homework. And this was homework 3. And when I say common errors, I mean exactly the same errors. I saw an awful lot of students with these wacko well, I should call them wacko, but they're very awkward to use. And they didn't compute. A lot of students didn't compute them. That's no good. You know, quotient like that, it's nice. It's nice on your scratch paper, but not in your final answer. You don't want to do that. All right, and so I took points up. Okay, good.
There's enough for each group.
I think so. 1 for each person is what we want to do. But you know, the thing is, so I took points off for students that didn't compute here, and I think those numbers are righteous. But don't give me stuff like that. All right, but the main thing is, these were identical errors. All right, so that means everybody was. I don't know. Is there a group me going? Is there a group me group going for this class? Because if it is, you won't be able to use it on the quiz. So if you're doing this like this, or using an example in the book like this to do your homework, and you don't know what you're doing, and obviously you don't realize what you're doing, you don't realize that what you're turning into me here is numbers everywhere. If you don't understand what you're doing on the quiz, you're going to be dead. All right? Now, studying on homework with your friends is normal, but there were for the 30 students that I graded, there was at least 10 that had this. So that means that a lot of you probably had this strategy and you didn't execute it right, and you're gonna get, because I'm gonna be grading everybody on the quiz. Now in the midterm, Tyler's gonna be grading some, and I'll be grading some, but on the quiz, it'll be me. All right? And here's another common error. I saw a lot of people with a parabola and the angle measurement sketched in from the x-axis up to the parabola. That's no good. You can't do that. That angle's undefined. You can't define an angle is a measurement between two rays whose termini are concurrent at the same position. And a parabola, the slope is changing at every point of the parabola, so you can't give it a unique angle measurement. If you were to, you got a question? No. Okay. Okay. No, I was the blue shirt. Were you saying something about your? I mean, yeah, you didn't. Did I slice your grade for that?
Yeah, you did.
Yeah. All right. So that's why I do it. You can't. There were a lot of. Now this was not from. This is to me. This is kind of. I don't want to say lazy, but ungraceful labeling. And you know what? I did see a bunch of you wrote in the parabola, and it was, it's kind of a wobbly parabola. But then you drew in the velocity vector tangent to it at the origin. That's the place where that initial launch velocity vector, 45. That's where you could put the 45-degree marking. All right. Now it would look very nice, but some of you guys did that, and I didn't mark it off. But this, no good. All right. So my admonition to you is, this wasn't nearly as common as this other. You know, look at over here. Let me get my gigantic cursor over here. Look at this stuff up here. I mean, all this stuff. Those are formulas from the book. And I got tired of writing down book. But you can't. You know, just looking up a formula in a book and then not knowing what the dickens you're doing with it, you're going to be SOL on the quiz and on the midterm, and you're going to crash and burn. And then you're going to have to, you engineering majors, you'll find yourselves, you know, doing the dreaded business major maneuver. Because remember, this is a washout class. This is a weed out class. And I'll be, you know, I don't want to weed out anybody, but it's going to happen. Probably. And, you know, the fewer the better, but, you know, do not doubt me. You know, you have to be able to think. And that's why going to office hours with Quinn, office hours with me, and I have office hours on Monday. What are yours on Monday?
4:30 to 5:30.
Okay, so mine are 11 to 1 on Monday. All right, in PS 158 in the Physical Sciences building, right by the main entrance. Quinn's in the same building at
4:30 to 5:30.
4:30 to 5:30. That kind of interaction will help you, and also your interaction with your classmates here. All right. Now, in here on regular class day, interacting and having common errors. I mean, having common errors is okay if you're working together on homework or something. It happens. But I don't want to see common errors on exam day. All right. So working with your team of three, whatever, you know, whether it's the chimera ants or the not afraid to square, no, not squared to calculate, or the team dad. Where's the team dad? The team dad meisters over there. Okay, the DADs, the area code 954s, the mighty 954s, or any of the other groups. You know, so use those. I've tried to set those up so that there's a variety of students in each group, and hopefully you can benefit in class. But on exam day or quiz day, you're on your own. All right? You won't be nobody in the same team will be working on the same problem. So you won't even want to look at their paper. Now, I'm not looking at anybody. I'm just saying, do not bother even looking at your neighbor's paper on Tuesday, because it'll be designed to reveal cheating and throw you into the SOL category. You know, and you don't want to be there. So you just do your own work. And you know what? Do your own work and give me your best. And don't be surprised if you get more than you think. You know, if you feel like, you know, the only way to get zip zap, I shouldn't say that. I mean, but the guaranteed way is to not do anything, of course. You know, and students sometimes do that, believe it or not. But give me your best on Tuesday, and let's see how that goes. All right? And by the end of the semester, on the final, I'll be telling you the same thing. Give me your best, and you'll be able to look back to quiz 1 and the final, and you'll be able to say, boy, I'm really starting to get this down. You know, because the problem that we have on quiz 1, you might have something similar to that on the final, because the final is cumulative. So, all right. And you're going to have to work faster on the final. You know, we're going to have a half hour for quiz 1. That's a ton of time for one problem. On the final, you have 170 minutes, 2 hours and 50 minutes. And you're going to feel like you don't have enough time, because you're going to be working really hard to get all the problems done on the final. But the more you can study and interact with me, with Quinn, with Kendra, with Tyler, with your team, the more confident you'll be, the more accurate you'll be, and the more quickly you'll be able to work. All right, now enough of that. Let's do some multiple choice IQ questions. So a little mental IQ test here. Let's see if your brain is cooking. All right. Now these are multiple choice. So let's just see what you can tell me about this one. Now I haven't drawn in the velocity vector for a reason, because I want you to describe its geometric properties with A, B, C, D, or E. So go ahead and vote for that. Can you guys make it count, please? 15 seconds to vote, starting now. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. All right, now we got some splaining to do, because these are the answers that you sent in, and C is the correct answer. The velocity vector is always tangent to the path. That's what a velocity vector is. You define the path, and then the tangent vector to that path, if the path has a time parameter, so a low value of time and then a high value of time along the path, it's a tangent vector in the direction of increasing time. That's velocity. So it's always going to be tangent to the path. All right, now let me get this. Now, those of you that, go ahead and make a note on this. Some of you, in fact, the majority of you voted for tangent to the curvature. Now, you may have been thinking this. You may have been thinking tangent to the path in your mind. You might have been thinking about it visually that way. However, curvature is not. Curvature is a number. Okay? In fact, it's defined as 1 over the square of the radius of the curvature. So it's measured in inverse square meters, meters to the minus 2, and it's not something that has geometric properties. It's a number. Okay, so you can't say it's tangent to it. You can't say it's perpendicular to it. You can't say it's parallel or anti-parallel to it. You can't do anything like that. So D is out. Parallel to the radius of curvature. No, that would be centripetal or centrifugal. Either parallel outwards or parallel inwards. Perpendicular to the path. No, always perpendicular to the curvature. There's again, A is. I see 3 of you voted for A. Yeah, perpendicular to the curvature. That's like saying the vector is perpendicular to the number 7. Or it's perpendicular to 3.209. You can say that, but it doesn't really have a meaning geometrically. All right, next question. About the acceleration vector. Let me get this one started for you. Okay. What's the description of the acceleration vector? And I only have 4 options here, A, B, C, or D. Uh-oh. Let me make this smaller. This answer pane is a pain. Okay, 15 seconds to vote. What's the count? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Actually, let me blip out of this. That would be the answer A, always perpendicular to the path. However, what do we know about the velocity? Velocity is tangent, but what about the length of the velocity? Do we know about that? If it's not a uniform, this one's not a uniform circular motion. Uniform circular motion, constant speed, constant radius. Okay? So the answer to this one is actually sometimes perpendicular to the path. Okay? And my next question is specifically about that sometimes business. All right, now hit the refresh key. And let's type in a short phrase or a word to describe what would happen with, come on, let me get my vector in there. So there's your velocity. With this, what would happen with this acceleration vector? How would you describe the motion, or how would you describe the velocity vector changes? And I think you only have 14 characters, so you can't make a really full answer. But let's see what you got, and we'll look at the answers to this. Nobody's voted yet. Listen to all the clicking. Now, talking it over with your neighbor is fine. Now, but not on Tuesday. You know, what is your guys' team? With the letter pi. Nice. The mighty pythons. Tanis, what is your guys' group's name? What? Betterer. Okay. Mahmood. No, wake up. Wake up your neighbor there. Come on, man. Stay awake. You're burning my grits. All right, let's look at your answers now. This is good. I see people going like this and pointing at stuff. That's good. I love seeing that. You got it? What is your guys' group's name? A2. Oh, I get it. A2 steak sauce. Very nice. instead of A1 steak sauce. Mad Lads. You guys getting an answer figured out or what? Yeah? Okay. Good. Joshua, you're back there at the back table. Gang. What's your guys' group name? Back table students. All right. The team of 4. 4 brains are better than 3, usually. Okay, 1 more minute. Anthony Brown. Is he asleep? Don't sleep. Stay awake. It looked like you were really, you were just, doozing and snoozing there. Come on, Mahmood. It's daytime now. It's not sleepy time. Cookies and cream comes after class. 50 seconds, starting right now. 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. Come on, you slackers, get it in there. Hit the send key. Come on. Okay. You're going to miss 2 points. Every question here, if you get it correct, is 2 points. You get 1 point for participating and 1 point for getting it right. So you either get 0, 1, or 2 for each question. Right? But you can't get any points if you don't send one in, and there's 5 people that haven't. So tough noogies. All right, now let's take a look at some of these answers. All right, and let me get this a little bit bigger. A velocity Willem. Whose answer is that? What were you trying to say? Go ahead and say it in English. Whose answer was that? Okay, we'll skip over that. Becomes wider. No, a velocity vector is a vector. It's one-dimensional. You can't call it wide. Something that has width, height and width can become wider, but not a vector, so that would be wrong. Constant is definitely not true. It's not constant in direction because it's got some acceleration perpendicular. I mean, look at the velocity, acceleration vector. It's got some perpendicular to the velocity, so that changes the direction. It's also got some in the direction of the velocity. So there's a few meters per second squared parallel to v. Now, when that's the case, what happens? It gets faster. So let's look and see if we... Okay, so we got change direction. So these 2 are right. All right, and this is wrong. Let's keep going down here. Now, the nice thing about this is this is okay. Change direction, changes direction, changes directio, changes directium. Whoever that is, you better get your X-ray specs for the... I get it, though. Constant with different different direction. Okay. Let's keep going down here. Anyways, now, if you have a question like this on quiz, here's the thing. On quiz 1, I haven't written it yet. I won't write it till after class, starting after class. But if I ask a question like this, where you type in a word or something, it'll be more than 1 point. So this might be a 2-point question. All right. So these guys up here with something that's dubious, curves. Yeah, I guess downward. No. Steve, you beg to differ?
Well, in that particular instance that you showed on the board, yes, it does curve downwards, but then afterwards it's going to curve upwards. But just in that picture
All right.
shown, it curves downwards.
I don't know what that means. Decrease. But what's decreasing? You gotta specify what's decreasing. Direction. Now wait a minute. Now how does it change? Okay, so direction is good. Doesn't change. Wrong. Downward. Okay. Fast. It changes fast. How does the velocity change? Fast. No good. Let me try to get down here. You can see that there's a lot of different ways to answer. Faster, okay. Go slower, wrong. Increases, not precise enough. What's increasing? Increase magnitude. Wait a minute. Increasing the magnitude of the velocity vector? What's that the same as? Increasing the speed, yeah. All right, so this one's good. Increase velocity. Yeah, okay. It's bigger. It's a bigger vector question. Yeah, you could have put in. You should have put increase, and then like an abbreviation. You know, increase V. You could have put increase V, and that would have been true. Okay. But no, the velocity vector has more than a speed. Speed V, but also direction. So you have to. You could have said no. You could have said change direction, change gear. We already went through all those. All right. So now remember all this. You know this is. Get what is your name again? David. David what? David O'Donnell. Getting this wrong is like not even a mosquito bite because we're gonna have tons of points and stuff. But if I did something like this on the quiz, hint hint, try to load as much information into your answer as you can. So that means use an abbreviation for increase, incur, INCR period, and then a space, and then something that's increasing, which the speed is increasing. Increase and change. This one, increase and rotate. Okay, this one I like. This one I don't. Increase and change doesn't tell me what is increasing or changing. The second one, increase and rotate, does. It implies increasing the speed, rotating the direction. See how that goes, David? You could have said, rotating. All right. And and the thing is, because I'm a human, I can understand all this. Larger vector. Oh, I like that. What's changing? Magnitude. Okay, the magnitude is changing. That's good. More left of. No! It's still on the. It's got no acceleration to the left. So I don't know what you're talking about on this one. More left of the line. More X, less Y. Let's look at that. More VX. What is it now? More X, less Y? less what? Yeah, okay. All right, so that component-wise. And I don't know what that is. New direction, okay. New deer. No change. Wrong. Nothing. Perpendicular TQ. Ooh, look at this one. Percuportional. Porcupine portional. Proportional to what? See, this one would be good if you could tell. Now, granted, you know what would be good on the test? A code table. Because then with a code table, you could, with 14 characters, you could type in just what you want if I write the code table properly. But for this one, proportional, you got to tell me proportional to what? Okay, now rolls faster. Okay, that's increased velocity. Same, no. Slows, incorrect. It doesn't slow, it gets faster. For this one, there's some acceleration. Whoops. Look at this thing. All right. There's some acceleration parallel to the velocity and some perpendicular to the velocity. So when you have, as I said before, when you have acceleration parallel to the velocity, like when something's coming down, when the baseball's coming down off its arc, it passes apogee. Now the acceleration is downward and it starts acquiring downward velocity. Okay? But it definitely doesn't slow. Question?
With that acceleration vector that's shown,
Yeah.
the speed would be constant, right? But
On this one?
if you keep
No, the
moving
speed
vector
is
up,
not constant.
If you keep moving the vector up,
You know what?
parallel to it would increase at that.
The acceleration vector? If you tilt the acceleration vector more closer and closer to parallel with v,
Increases.
yeah, then that would be. But then you don't have any. The problem with this is, you know what this physically corresponds to? This corresponds to you in your car going through this turn and hitting the gas and staying on the path. That's what it corresponds to. All right. So the fact that now, what is your name again?
Angel.
Angel. So Angel, the fact that we've got some meters per second squared parallel to v here means he's hitting the gas. Think of it that way. But if he's on the path, he has to have some meters per second squared perpendicular to the path, right? Because it's a curved path, all right? Now, if he doesn't have any of that, he goes, if he loses all perpendicular meters per second squared, that means his tires are no longer gripping and he's going to go off the path and, into a tree or something like that, or hopefully into a snowdrift, all right? But if he stays on the path, on this path, you're going to at least have some perpendicular meters per second squared to change if not the speed, then definitely the direction. I mean, if he goes through this curve at this set of curves at like 20 miles an hour, the acceleration is going to be bigger and smaller in places, but always perpendicular to the velocity.
I can say that
All right.
with the car example.
Yeah, the car example. So now let's take a look at some of these other speed increase, righteous, steeper. Doggone this thing. Let me move this out of the way. Steeper. No. To A. Toward A. Oh. Toward the no. That doesn't make sense to me. Turn to A. No. Turns. Yeah, okay. Up. Not enough. 2 letters, but you had 12 more you could have typed in, so let me try to get this. Come on, baby. Well, we've gone through quite a. Oh, this must be the last one. Up. That's the last one. Is there? All right, let me get out of here. Try it again. All right. See, I don't. All right, here we go. See how this is all blooped up? This software. Well, I'll grade the rest of them later. But anyways, we got a flavor of, how to think about this. And believe me, this is a this is shh, 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 shh. This is a kind of question that if I give it on the quiz, as part of the 6 multiple choice, it's going to cause you to think, and especially if I give you a short word or a short phrase or a word, and especially if I give you a code table. Now, I'm not saying I'm going to do that, but I do that on quizzes and exams and stuff. So be ready. And as always, as I've tried to communicate to everybody, you want to be able to think about what's actually happening. So like Angel was saying, yeah, the car example makes it makes it easier to understand. This is kind of abstract here, but once you think of this as a car, then you can think about what a car does. Hit the gas or hit the brakes. If we were hitting the brakes, we'd have something down in the 3rd quadrant. This is 2nd quadrant acceleration. All right. Now, 3rd quadrant, you'd still have some perpendicular meters per second squared at this location anyways, but you'd have some slowdown acceleration, some meters per second squared anti-parallel to the vector, therefore slowing it down. So your speedometer would go down a little bit. So what I'm trying to get to see, you guys think about, quizzes differently than I do because, you guys aren't a teacher. You guys aren't teachers, but what I'm trying to do is interrogate your mind and see if you can think. That's it. And if you could think, are you thinking in a righteous manner to deliver an accurate answer? You got to build that bridge. You got to get that spacecraft onto Mars without crashing. You got to take that patient in the hospital. Did you know that a lot of physics majors and stuff, it's a good major to have if you want to go into med school. If you got to take a little biology and stuff along the way, but physics is actually pretty good for getting into med school. So you get into med school, you become a doctor, you got a patient, and you got to calibrate your treatment. You don't want to, because a lot of stuff, like chemotherapy for in my family we have some cancer patients, and chemotherapy, probably in this group of people, a few of you do as well. And if you do, then you know that chemotherapy, the medicine that they give you to kill cancer, almost kills you. It's so harsh, and so they got to give you enough to kill the cancer, but without killing you. And that's a calculation, based on your body mass, your kidney, all kinds of things that they got to factor in to give you the right dose. And that's a life or death thing. So that's losing a spacecraft that crashes on Mars or goes off into space or something. That's one thing. That's billions of dollars, millions of dollars. But what's the price of a human life? Infinitely more than that. So that's even more pressure. So you want to be able to think. You want to be able to think physically, and you want to be able to deliver an accurate answer, because lives may depend on it. All right, let's keep going. Question.
I want to know why the last question, number 2, acceleration isn't always perpendicular.
Because this is the case.
Yes, but
In uniform circular motion, it is perpendicular. But in this one, if you don't have perpendicularity, on a curved path, you've got some speed up or some slow down. And so if I tell you that it's uniform speed, then you know always perpendicular. But I didn't say that. You know the previous question? I just said on a curved path. I didn't say anything about what the speedometer said. All right? If you know it's uniform speed, you know, even if it's not a circular path, but uniform speed, the acceleration is always perpendicular. It's only changing the direction. But if, now what is your name again?
Cecilia.
Cecilia. And your last name?
Pavoni.
Pavoni. Okay. Cecilia Pavoni, if you have an unchanging speedometer, perpendicular. But if you have some slowdown or some slowed up as you go through the curves or on this, you know, even on the circle, you know, you can have a perfectly circular path and you can slow up and slow down. You know, like on the Nardo ring. I mean, that's you know, cars on the Nardo ring, they don't have to go at 149 miles an hour. They can go slower or faster, you know, and still stay on the ring. So they'll have perpendicularity to keep them on the ring, but they'll also if they're speeding up or slowing down, you know, like if they're speeding up to 149, you know, then they're going to have something like this. All right, Derek.
Does it not change direction like immediately to the?
It's continuously changing direction. And here's another thing, you guys. A small delta t away from this is a snapshot. A small delta t away from this, you might have a different, you will have a different velocity vector. It'll at least be tilted. It might be, in this case, it will be longer. So because this one's speeding it up. But the acceleration might change there too. You might, in other words, you might let up on the gas. You accelerate for a little bit of time, and then you take your foot off the accelerator. All right? So does that make sense to you, Derek? Does that answer your question? Good? Okay. Robert.
So, just a quick
See this? I'm learning names. I'm learning names. Cecilia and Andres. See, I'm learning you guys' names. Okay. So, and David back there. And what's your guys' group? Yeah. The dad group, yeah. David and who's the other D? What's your name? Daniel. And you're what's your first name? You're in the dad group, right? Yeah. Oh, so it's just the D. Oh, that's right. David, Daniel, and Andres. That's the DADs, the dad group. Okay.
So just a quick clarification. So if the speed was decreasing, would the acceleration vector then rotate towards?
Yeah. The question was if the speed was decreasing, slowing down, then the acceleration vector would be, you know, pointing southwest somewhere.
Yeah.
You know, you'd have a little bit of meters per second squared back this way. So that'd tilt it to the other side of that that radius, that dotted line. See the dotted line radius?
Right. So
Okay.
does
So
that
it'd be on the opposite side of the radius.
So does that mean that like the more speed that we're either increasing or decreasing, the more extreme that angle then between the acceleration vector and the velocity vector?
No. The more. Okay, so your question was
So if the
speeding up a lot or speeding up a little bit.
Yeah, if the
Okay, so so the question is, what if you really put the hammer down as you go around this curve? All right? Right. All right. So you hit the gas. Now what that means is you've got more meters per second squared in the direction of V. So that's going to rotate V closer and closer, but it won't be, if you're staying on that track, it'll never be parallel to V. But it'll be getting, in this case, it'll be getting closer and closer to about 30 degrees, but you'll never get to 30 degrees if you're on the track. Okay. Yeah, and then so that means that the magnitude of the acceleration will be bigger as well. Because you on this track. Here's something else. At this instant of time, you always have to have a certain number of meters per second squared. No, that's not right. Because the centripetal acceleration is v squared over r. So this would be an interesting one to map out, how that vector would change as you increase the gas or as you hit the brakes. I'll have to work that one out. I'll have to. Did you guys see that diagram I posted in discussions? I worked it out. Let's take a look at it. Can you switch me over to the computer, please? All right. Yeah, and I also put it in announcements. But yeah, so here's the, and this is pretty precise. It was the perfect shot was off by less than half a meter at a distance of 15, 18 miles. That's pretty good. So that's the red one. So I plotted. It's pretty easy to do this on a spreadsheet, and here's the first shot, and I continued both of them as far as 23,750, and then I thought, okay, that's enough. But you can see that the first shot, it would burrow, if it could, it would burrow down into the mountain, and it wouldn't hit the aliens. And it hits slightly uphill here, so, and you can calculate that. You can calculate that point. Steve?
You said for the triangle thingy, we could make it either a triangle or like an upside down parabola. Like looking at it that way. Maybe not.
I don't think I ever said anything like that. I can't think. The triangle here is the volcano.
Yeah.
So, and then this green blob up here is the aliens, because aliens are always green. So, anyway, let's go back to the laptop. Now, I want to give you. We're done with clicking for the day, so you can put your clickers away. We're gonna. Can you hand out paper? Just hand it out in bunches. We're going to do a problem. You're going to do a problem together as your group. This is your classwork for today. So put your name on it and.
Individually, or are we turning one?
Yeah, one for each student. Everybody's going to do this classwork. And the problem that we're going to work on is this one. Given a tennis player that sends the ball at an angle of 32 degrees with a velocity of 25 meters per second, up towards the stands, and somebody catches it at an elevation 7 meters above where it started. What's the amount of time? Calculate the flight time, and then the velocity vector at the moment just before it's caught. All right, so go ahead and work on that. And we'll take a good 20, 30 minutes on this, so do a nice job. Okay, students. Let's go over the solution here. Here's kind of a rough sketch that we put together. And for those of you that got dinged for the the angle measurement incorrect on the homework, it should look something like this. I made my launch angle, my launch vector in red, and I made my angle notation in red. And it overlaps the actual parabola, so it's not ambiguous. So what we have here is basically a parabola, and we're assuming that the fan is at the first place where it can catch. Now, on the diagram that I gave you, the fan was over on this part of the parabola, but I'm going to solve it for this one. Now, if you did it over here, that's all right. I did it here, so this is like a total line drive. All right, direct hit, no up and over if you catch it here. And the reason I did that is because it's the closest. All right, thank you. All right, now I'm looking at your guys' papers here. They look pretty good. So, oh my goodness, the DADs. I don't know this parabola. You're not going to get marked off, but the parabola's looking a little shaky. I don't even. The 954s. I don't see a parabola on this one. Oh my goodness. Y equals Chris squared plus 1. I must rebuke that parabola. Just say no. All right, so maybe do a little parabola sketching practice if you want. Here, take this. Let me switch you over briefly to look. Switch me to the doc cam again. All right, so here's my doc cam work. Let's take a look at it. And use my probe here. Okay, so here's your basic. I take it back about. Now, who is it that I gave? Chris squared plus 2. Chris squared plus. Where are you at? Chris squared plus 2. Okay, I'll give you a reprieve because mine's looking a little shaky here too. But this is actually closer to that first intercept point. Can you give me that screen again? Because this is the solution that I calculated, and it's on the upswing. This one's pretty close to the top of the parabola. But we're going to let the numbers do the talking, as I always say. So here's your first move. Figure out your components, 13.24 meters per second for the initial value of the y component of the velocity. Now, the x component of the velocity is 21.2 meters per second. And hey, you guys, it does not change. Right? There's no such thing as horizontal gravity. So when you're trying to figure out the velocity up here at the catch point, point C, this is gonna be the x component of it. Now, the y component of the velocity does change, so you're gonna have to deal with that. Now, here are the two equations of motion for x of t and y of t. And that's just like we did for the homework. Okay, homework 3. And now on this one, I use quadratic formula to solve for it. So I put in the set height, 7 meters. And so I said solve for 7 meters equals Vy of 0 times t, subscript c, minus 4.9 meters per second squared, times t subscript c squared. All right, and so it gives you a quadratic formula that looks like this. You plug in your numbers, and there's the quadratic formula in general. And now on this one, you have 13.24, so that's minus b. In the way that I wrote mine, that's a minus 13.24. Okay, all right. And, or I should say, this coefficient up here is negative 13.24. In the quadratic formula, it's minus b, so this becomes a positive 13.24. And then you got this obnoxious square root, and there's nothing to do about obnoxious square roots in the quadratic formula. You just got to crank them out. So 13.24 squared and then 4 times AC here. It's not that difficult. But here's the problem. The plus and the minus give you two solutions for the time. This is the time on this parabola. It takes a certain amount of time to get to 7, and then it takes you another amount of time to get back to 7 after you pass the apogee. All right? So here's how you figure this out. You got two solutions. Okay? Now, the earliest intercept time is going to be the one with a minus sign here, where you subtract the square root. So I symbolize that t subscript minus, and that's my first intercept point, and that's the one that I assumed. This comes out to 0.7199 and then a bunch of stuff. Okay, 0.72 seconds approximately. But the back of the volcano, the other side of the parabola, I didn't specify if it was this one or not. And let's see, I didn't calculate that out. Who calculated this out? The second one. Who's got? Okay. What have you got? 1.98. 1.98. Anybody verify that 1.98? Okay. So 1.98 out here. All right. So that's good. And notice that. Notice that it's not double. It's not double the time. All right. Now there's a secret way that you could figure out the first intercept point, and that is to figure out the amount of time it takes to get to the apogee. All right. So the rise time to get up here to apogee, and then figure the amount of time it takes to drop, and figure out the height of apogee, which you can do. And then figure out how much time it takes to drop down to 7 meters. All right, and then subtract that from your apogee time. So you could have done that. That's a little bit more work, but it does avoid the quadratic formula. Anyway, so here are the two physical solutions. Now, hey, you guys, when you're doing a problem like this with a quadratic equation of any kind, and you're trying to find solutions to it, remember, one of the solutions might not be physical. All right? In this case, either can be physical, depending on where the stands are. All right? So anyway, so here's, and then down here, here's the calculation at time t subscript c, 0.72 meters, 21.24. Is that what that is? No, 21.2 even meters per second. It doesn't change because there's no such thing as horizontal gravity. But there is vertical gravity. So you have whatever you start with, Vy of 0, and then you subtract 9.8 meters per second for every second of free fall. And so for us, it's not a full second, it's 0.72, and that works out to 9.71. Anybody verify me on that? 9 point, okay. What's that?
Used half its gravity.
Oh my goodness. Dr. B, all right, this good thing this is in pencil. All right, wow. So this should be negative 9.8. Dr. B. All right, let's figure this out. 0.72 times 9.8 negatory plus 13.24. 6.18. Anybody verify that? 6.18? Yeah, okay. Good. 6.184 meters per second. All right, so that's, and my final note on this is it's positive. All right? So it's still going up. And that means that, yeah, you're up here. You're on the upswings. You're still up here. It's still going up. Now down here, you would have a negative 6.184 for the speed, for the vertical velocity of the speed down here, or the vertical component of the velocity. All right, because it's going downhill. But you still have the same horizontal component. All right. And so actually, those of you that figured out the velocity over here at whatever it was, 1.98, did you get negative 6.18 over here? Yeah, okay. So for this kind of a solution, the velocities are symmetric. The times are not. All right. Actually, the times, you know what the times are? They're symmetric about the rise time. So here's your apogee. The amount of time, so you know what you could do? 0.72 plus 1.98. Is that what it is, 1.98? So that's 2.7. So the time to apogee is 1.35, halfway between these two. Can somebody verify that? Yeah, how could you, did you do that? Did somebody do that? The apogee time? Who did? You guys? Over there? Yeah. Okay, so 1.35, the apogee time. Yeah, good. Good. All right. So that's that one. Now, that's a good reinforcement, and you even saw Dr. Brickner get caught napping on this negative 4.9 down there. Now, that's all right. And you also saw my semi-nasty parabola. Question?
So at the 7 meters off they're off
Hush everybody. I'm listening to a question here. Go ahead.
are we finding the y
Well, repeat it from the beginning.
from the like how we were finding the answer 7 meters height, like whenever it reached 7 meters?
Yeah.
Were we finding the y component velocity or the actual velocity with the
You mean the speed,
yeah.
the overall speed. Well, that would be the Pythagorean theorem of these two down here. 21.2 quantity squared plus 6.18 quantity squared.
So is it
Add them together and then square root that. What did that? Did you do that?
oh no, but I was thinking like we got a different answer because we thought you had to find the actual like component y's velocity combined. So not just the y component, but the x and the y.
Well, this is how you do that. These are the two components. You don't mix them together. You calculate one and keep it separate. You calculate the other and keep it separate. And then maybe do Pythagorean theorem to get the magnitude of the vector, the speed. All right, now, can you swap me back to the laptop? We're going to do a little bit of instruction now on circular motion as oscillation. I'm going to do it on the document cam, but I'll embed the images in the YouTube. Can you switch me back to doc cam? All right, now, can you give me my blue pencil from over there? Pen, yeah. All right, go ahead and make a XY, XY coordinate system. And let's make a nice size circle. So let's see, this is the origin right here. I'm going to make mine 5 units. So this is 5, 0. And then 5 units up. This is 0, 5. Then 5 units left. 1, 2, 3, 4, 5. So this is negative 5, 0. And then 5 units down. 1, 2, 3, 5. Just for nice round numbers. 0, minus 5. Okay. So this is another oscillation situation. This is page 1. We're going to do about 3 more pages. Now, try to sketch in a nice circle. And the thing about the circle is tangent to vertical lines side to side, tangent to horizontal lines high and low. So try to make it as nice as you can. And Team DAD, I'm not going to come over there and supervise, but wait a minute. This is too big. Doggone it. All right. Let me do mine again. You see how it works? You try to do something nice, and you mess it up. Okay. Okay, so here's my circle of radius 5. See that right half was looking a little bit gigantic, so this one looks a little bit more righteous. And you know, if you have a compass, you can do that nicely. Now let me fill that in with the blue ink. So it's nice and visible. All right, so this is 0, minus 5, 5, 0, 0, 5, minus 5, 0. Okay, so there's my circle on the XY plane. And now I want you to choose a dot in the first quadrant, any place you feel. I'm going to make mine up here above 45. Just choose a dot, any dot. Can you give me that protractor? Okay, and I'm going to draw in a radius back to the center. Okay, and so this is a radius of length 5. And draw a dotted line down to the x-axis. All right. And let's just call this x of t, comma, y of t in parentheses for that point. All right. And I'm actually going to measure this angle a little bit. So let's see, this angle is this angle is about 63 degrees. Okay, so this is a good angle. All right, now we're not going to worry about the actual size of that angle. So what we do want to do is put in theta. Now, if this is uniform circular motion, then theta changes uniformly with time. 2 pi radians, and you guys, I'm switching over to radians now for this part of the discussion. Every t amount of time. So the period is t. So capital T is the period for circling. All right, and theta changes from 0 to 2 pi in, so if t is 1.5 seconds, then in 0.75 seconds, theta changes by pi. In 1.5 seconds, it changes by 2 pi, et cetera, et cetera. So theta as a function of time is equal to 2 pi over capital T times to the time parameter t, little t, okay? And 2 pi over t is also known as the angular frequency omega. All right? So the position, if you think about this, let me write up here r equals 5. And we'll just use no dimensions here. So this is like a math exercise without any. So this could be 5 centimeters or 5 light years or whatever. This symbolizes uniform angular motion. If it's going on a circle, then it's uniform circular motion. All right. So let's write down x of t is equal to, all right, so that's this right in here. There's my x of t. And this is just kind of a generic position up here. So that's equal to r times the cosine of theta. All right? Now that's a function of time because theta is a function of time. So we can rewrite it as, and let's put in 5 times the cosine of omega t. Right? So there's your time dependence for the x coordinate if the origin of coordinates is the center of the circle. Right? Now, it doesn't have to be, but if that's what you do, then it's good. Right? Similarly, y of t is equal to 5 times the sine of omega t. All right? All right, so that's for this circle. Now, I want to just go and do a general form for those two equations. So let me do that on the next page. Okay. I'll put my earpiece back in. Hold on a second. Okay, so let's do this a little bit more generally. A circle of radius r, uniform circular motion, and we'll give it angular frequency omega. So x of t is equal to, in general, r times cosine of omega t. And y of t is equal to capital R times the sine of omega t. All right, now that's if you choose x of 0 to be 0 and no, x of 0 to be capital R and y of 0 to be 0. So that's if you choose the time scale to start right here. So the initial position. So that's r comma 0. Okay. So now if you want to study something that starts at 12 o'clock, yeah, then you'll have a slightly different set of equations here, but you can do it. Now this is the simplest one to work on. So like, so this will work, okay? Now, let's do the derivatives. dx by dt is equal to, okay, cosine is a negative sign, right? So this is minus omega, derivative of the inside, times r, times the sine of the stuff inside. Okay? Now d by dt of y, and now sine is positive, so this is positive omega r times cosine of omega t. All right, now let's figure out something about this. So this is Vx of t equal to minus omega r sine of omega t. And this is Vy of t. And notice that this one, there's no constant here. We're not in free fall. We have a physical constraint in 2 dimensions. Okay, so it's not like free fall where you just have a constraint or a force in 1 dimension. Here you've got something so it might be, like a wire or a track or something that's circular, and the rigidity of the track is what keeps it in a circle, all right? And for that reason, we have things that change, both coordinates change in time. So it's a little different from free fall. Now let's try something, Vx squared. Vx squared, and I'm going to drop the time dependence in there. That's going to be omega squared r squared times sine squared of omega t. And Vy squared is going to be omega squared r squared times cosine squared of omega t. All right, so the speed, which is the square root of Vx squared plus Vy squared, is just going to be equal to, square root of, a big square root, omega squared r squared, times the sum sine squared of omega t plus cosine squared of omega t. Close bracket, close square root. All right, so there's our, now what's that sine squared plus cosine squared business? It's 1. So we don't even have to write that down for the next level. And what's the square root of omega squared r squared? Omega r. So V is equal to omega r. Okay? And you guys, whenever you have an oscillation, you're going to have the speed. You're going to have some, especially if it's if you're working with the forces and stuff and accelerations. There's going to be some kind of a physical speed, which is your angular velocity omega times the amplitude. In this case, r. All right. So now let's try to draw a sketch of this. Let's make another. I'll make a big circle here. Okay, and let me make 5, 5. Let me just do the first quadrant. And we know that omega t is right up here somewhere. Okay, so my position vector, so this is, let's call this lowercase r of t. Okay, for position vector r. Okay, now v of t is equal to vx of t times I hat plus vy of t times j hat. Okay. And what we're going to do, let's think. So this is sine of omega t. So this is minus v sine of omega t times I hat plus, I'll write this down the next line, positive v times cosine of omega t. Okay, so this is like, in terms of proportional triangles, this would be the horizontal, and this one up here would be the vertical. except this is j hat over here. Okay. So this is proportional to the so here's your original triangle. Okay, here's your position triangle. Okay, now we're going to attach the velocity vector up here. But we want its vertical part to be, it's going to be similar to this triangle. Because this is an omega t triangle. Okay, so this big angle, the big acute angle down here is omega t. All right. So this v is going to be an omega. It's going to be proportional to this one, but the vertical part is going to be positive, and it's going to be small. It's going to be so. This is the small side. The horizontal part of. So let me write that horizontal part of the R triangle. Okay. So I'm going to go up a little bit. Let me try to sketch this in. All right, so let me make a, okay. So there's Vy of t. Now, the other one is going to be negatory. Okay, minus v. V is a positive number. So this one, it's going to be proportional to the vertical part, all right? So it's going to be the long side, but it's going to be negative. So this one, so here's the component, okay? There's Vy of t. And then tip to tail, let me draw a nice big, there's Vx of t, all right? And we draw this in. And there's your V of t vector. I'll do that one in red. Can you give me my red ink pen? Right. So here's your, and this is just kind of eyeballing it in, but you can see, my wonderful students, that V of t is perpendicular to R of t. It's perpendicular to the radius. All right? And how did we get this? Derivatives. If you know the path, you can always figure out the tangent vectors. All right? Now, let's do another derivative. So this triangle, I'll kind of shade it in red. Okay. I'm going to go to the next page. So this is page 2 of today. Here's page 3. All right, so Ax of t is d by dt of Vx of t. Okay, so that's d by dt of minus V. Now, what was it? V times cosine of, no, V times sine of, Vx of t was, Vx of t sinus minus omega r sine of omega t. Okay. So sine of omega t. Okay, and so that's equal to, okay, so I don't get another minus sign, so I get a minus, and there's a, so minus V times omega times cosine of omega t. All right? And similarly, a y of t, you got to do both, d by dt of vy of t, and that's equal to d by dt of positive v times cosine of omega t. And this brings out another minus sign. So minus omega v times sine of omega t. Now, my wonderful students, v is equal to omega r. So let's write this down. I'll write it over here. Minus omega r times cosine of omega t. And this is minus, actually that should be omega squared r. Omega squared r times sine of omega t. So ax squared plus plus ay squared, quantity squared, what do you think it is? What's that going to work out to?
Omega r.
Omega squared r. By the trig identity. All right. And so that's the centripetal acceleration. A subscript c equals omega squared r. Or you could put v squared over r if you want it in terms of the speed. All right. So a subscript c, as we mentioned last time, omega squared r or v squared over r. Okay. Now, if we do the same thing with the circular path again, here's my omega t here, and here's my initial triangle. This thing, look at this for a second. This is minus omega squared, or this is minus omega squared times y. And ax is minus omega squared times x. So that means that your acceleration vector here is toward the center. And how did we get two rotations by 90 degrees counterclockwise? Differentiation with respect to time. And this is one more reason to say that you have centripetal acceleration. In other words, not centrifugal. Now, I'm going to give you a little bit of a motivational blurb for your later classes. And almost everybody in here will have some kind of atomic or nuclear physics class, whether it's physics 3 or something higher than that. This rotation by 90 degrees is related to something called, switch me over to the laptop. It's related to something called the Wick rotation, W-I-C-K. The Wick rotation. And that is the secret of quantum mechanics, where you rotate your time axis to imaginary time, which is like a rotation of 90 degrees. And it's related to everything that we just did. Now, as I said, study everything this weekend. Be alert to what's in web courses. Be alert to what's in the textbook. All right, and I'll see you on Tuesday, maybe Monday for office hours. You're dismissed. All right, let's get this stuff ready. Man.
Did you pass out the follow-up
The what?
The homework three? Okay,
No, I haven't graded your guys' yet.
Oh,
So
really?
I'll be sending it to you through web courses messaging.
Thank you.
Oh,
So be alert.
Did you say you had something today?
yeah.
I've already,
yeah,
you can take that out.
Yeah.
I was off.
Yeah.
Okay.